Hello, let us have some examples for random variables. In this example, we introduce a uniform random variable. As example, application example, you can consider a telephone call which is supposed to happen in the interval of 0 to 1. Well, this could be a packet, a phone, everything else. And suppose that all real numbers between 0 and 1, so let's say here is 0, 1. This means that open from this side, this means close from this side. And suppose that all points here are equally likely. So the outcome of the experiment here is Xi. So Xi is a number between 0 and 1. Okay? And your sample space L is equal to 0 and 1. So this is the whole interval. Now, we could define a random variable such that x of Xi is equal to Xi, because we said that this is my L, the set of real numbers 0 and 1, and I want to define a function here. So if this is Xi, I map Xi to itself. This mapping is my random variable. So this is identity mapping. So this is a random variable. It has all it needs to be a random variable. So the variable in this example, because this is a real number, but in the case of coin or dice and so on, Xi was not a real number, so we needed to map it to a real number. So here is already, so it is also a random variable itself, so it has a double meaning. The outcome of the experiment is also the random variable. It's also a random variable. And the question is that, is this true for all random variables? Of course not. For instance, if you have a dice experiment, so you have this one, and then you have 2, etc. Of course, you could map this one to 1, map this one to 2, etc. And then this mapping could be a random variable, because we need here to be a real number. So for this example of phone call between 0 and 1, we want to show it is random variable. So in order to show that, we should be able to talk about its probability distribution. If we cannot talk about its probability distribution, we don't call it random variable. So first of all, x of Xi is a real value. And second of all, the CDF is meaningful. So therefore, it means that I have to be able to determine probability of x is smaller than or equal x. So obviously, this means that probability of all those X's, so if your x is here, so probability of this area, which is equal to this length divided by total length, which is equal to x, if obviously x is between 0 and 1. But if your x is negative, so probability of here is 0. So this is equal to 0 if x is negative, and is equal to 1 if x is bigger than 1. So, and then we call this uniform distribution. So this guy is probability that x is smaller than or equal a. So first thing I do is that for a bigger than 1, I have the whole sample space, and then probability is equal to 1. For a is less than 0, my event x is smaller than or equal to a. If this is negative, is equal to empty set. And probability of empty set is 0. And if a is between 0 and 1, the probability is going to be equal to that. So if you plot it, the CDF will become 0, 1, and here you have a very unitary slope here. And then we call this a standard uniform distribution, standard uniform. Or a standard uniform CDF, cumulative distribution function. So a uniform random variable in general, instead of being between 0 and 1, it could be between real number a and b. It could happen between numbers a and b. In that case, we say that the PDF, this is the derivative of CDF. So these d to dx of fx of x, okay? So, so if you want to look how it looks, so the CDF is, instead of starting from 0, it starts at point A and it ends at point B. Here it becomes 1, and then you have a line. So any CDF which looks like 0, 1 above certain point, and here is a line, we call it uniform, because all the points in this interval, okay, they are equally likely. The slope is constant. The derivative of this function, which we call it the PDF, probability density function, is constant.